Hey everyone! Tonight we're exploring one of the most mind-expanding topics in all of cosmology and physics, the incredible journey from the smallest possible measurement in our universe to the largest structures we can observe. Before we settle in for this cosmic voyage, take a moment to like this if you enjoy these deep space explorations, and let me know in the comments where you're listening from and what time it is for you. I always find it fascinating how our global community gathers to contemplate the cosmos together, sharing this moment of wonder across continents and time zones. If you're new here, consider subscribing to join our community of cosmic explorers. We gather regularly to examine the universe's most profound mysteries, not through dramatic explosions or alien encounters, but through the patient, methodical processes that have shaped everything we know. Tonight's journey will take us through scales so vast and so tiny that they challenge the very limits of human comprehension. Now get comfortable, dim those lights, and perhaps step outside if you can see the stars. Tonight we're not chasing dramatic space battles or alien encounters. Instead, we're going to examine something much more profound and peaceful: the extraordinary range of scales that exist in our universe, from the quantum foam that bubbles at the foundation of reality itself to the cosmic web that stretches across billions of light years. Let's begin our gentle journey into the infinite, where every step will multiply or divide our perspective by factors that dwarf our everyday experience. Imagine, if you will, that you're holding a cosmic ruler, one that can measure anything from the tiniest vibration in the quantum vacuum to the largest structures in the observable universe. Tonight, we'll travel along this ruler, pausing at each significant milestone to contemplate what exists at that scale and how it relates to our human experience. This journey will take us through 42 orders of magnitude, a range so vast that if you were to start at one end and count to the other using every second of your life, you wouldn't even make a meaningful dent in the progression. Our journey begins in a realm so small that it exists at the very edge of what physics tells us is possible to measure or even conceptualize. We start at the Planck length, approximately 1.6 × 35 meters. To put this in perspective, if you were to enlarge a Planck length to the size of a marble, then that marble, by the same proportion, would be larger than the observable universe itself. This is where our understanding of space and time begins to break down, where the smooth fabric of space-time that Einstein described becomes a churning foam of quantum uncertainty. At the Planck scale, the very concepts of distance and time become meaningless in the way we normally understand them. Here, quantum fluctuations become so violent that they create and destroy virtual particles in timescales so brief that they exist in what physicists call borrowed time, appearing and disappearing before the universe's energy-time uncertainty principle notices the violation. These are the quantum seeds from which some theories suggest entire universes might spontaneously appear. Picture yourself somehow existing at this scale, though of course it's impossible. You would witness a landscape unlike anything in our macroscopic world. Space itself would appear to boil with activity, with tiny wormholes appearing and disappearing, connecting distant points in space-time for infinitesimally brief moments. The geometry of space would fluctuate wildly, sometimes stretching, sometimes contracting, creating a foam-like structure that underlies everything we see in the larger universe. This is the realm where all the fundamental forces of nature, gravity, electromagnetism, and the strong and weak nuclear forces existed as one unified superforce in the earliest moments after the Big Bang. At this scale, there's no distinction between matter and energy, between particle and wave, between here and there. Everything exists in a state of pure potential, waiting for the universe to expand and cool enough for the familiar structures of atoms and molecules to emerge. As we step up our cosmic ruler by a factor of 10, we're still unimaginably small. But now we're entering the realm where the fundamental particles of matter begin to have meaning. At scales around 10-18 meters, we encounter the quarks and gluons that make up protons and neutrons. These particles are forever confined within the nuclei of atoms, bound together by the strong nuclear force with such incredible strength that they can never be separated. Here, at the scale of a femtometer, we find ourselves in a world where the rules are dominated by quantum chromodynamics, the theory that describes how quarks interact through the exchange of gluons. The colors mentioned in quantum chromodynamics aren't actual colors, but rather a property similar to electric charge, but far more complex. Quarks come in 6 flavors: up, down, strange, charm, bottom, and top, each with its own mass and properties. At this scale, we witness the birth of mass itself. The vast majority of the mass in ordinary matter doesn't come from the intrinsic mass of quarks, but rather from the energy of the strong force field that binds them together. This is where Einstein's famous equation E=mc² becomes viscerally real. Energy and mass are revealed to be different aspects of the same underlying reality. Moving up by another factor of 10, we reach the scale of atomic nuclei, roughly 10 to 15 meters or 1 femtometer. Here sits the dense heart of every atom, containing virtually all of an atom's mass, compressed into a space 10,000 times smaller than the atom itself. If an atom were the size of a football stadium, its nucleus would be roughly the size of a marble sitting at the center of the field. At this nuclear scale, we encounter one of the most profound examples of the balance between opposing forces in nature. The strong nuclear force, which binds protons and neutrons together, is locked in an eternal struggle with the electromagnetic force, which tries to push the positively charged protons apart. This delicate balance determines which elements can exist in the universe and which combinations of protons and neutrons create stable nuclei that can persist for billions of years. The nucleus is where the universe's heavy elements are forged. Through the process of stellar nucleosynthesis, stars spend their lives fusing lighter nuclei into heavier ones, climbing up the periodic table step by step. Iron 56, with its 26 protons and 30 neutrons, represents the peak of nuclear stability, the configuration where the binding energy per nucleon reaches its maximum. This is why iron is so abundant in the universe, and why stars cannot generate energy by fusing elements heavier than iron. As we continue our journey outward, we cross the boundary into the realm of the complete atom at roughly 10 to 10 meters, about 1 angstrom. Here, the nucleus we just visited becomes a tiny speck at the center of a vast cloud of probability, where electrons exist not as particles orbiting in defined paths, but as quantum probability waves that define the likelihood of finding an electron at any given location. At the atomic scale, we encounter the beautiful mathematical structures that govern chemistry and define the properties of all matter. The electron orbitals S, P, D, and F create three-dimensional shapes of probability that determine how atoms bond with one another. These shapes, spherical s orbitals, dumbbell-shaped p orbitals, and the more complex geometries of d and f orbitals, are not arbitrary, but arise naturally from the mathematics of quantum mechanics. The atom is where the quantum world meets the classical world, where the strange rules of quantum mechanics that govern individual particles begin to average out into the predictable behavior we observe in everyday matter. At this scale, the wave-like nature of particles becomes apparent. Electrons don't orbit the nucleus like planets around the Sun, but exist as standing waves with only certain wavelengths allowed to fit around the nucleus. This is the scale where the universe's complexity begins to emerge from simplicity. With just 3 types of particles, protons, neutrons, and electrons, and the rules of quantum mechanics, the universe creates the 100+ elements of the periodic table, each with its own unique properties and chemical behavior. Hydrogen, with its single proton and electron, is the simplest atom, while elements like uranium, with 92 protons and a similar number of neutrons, represent some of the most complex, stable atomic arrangements. Stepping up another factor of 10, we reach the scale of small molecules, around 10⁹ meters or 1 nanometer. Here, atoms link together through the sharing and exchange of electrons to create the molecular building blocks of matter. At this scale, we witness the emergence of chemistry, the dance between atoms as they form bonds, break apart, and recombine in endless variations. The nanometer scale is where life begins to emerge from inanimate matter. DNA, the blueprint of life, is about 2.5 nanometers wide. Proteins, the molecular machines that carry out life's processes, typically range from 2 to 20 nanometers in size. At this scale, we see how the precise arrangement of atoms determines function, how the shape of a protein determines its ability to catalyze chemical reactions, how the sequence of bases in DNA stores the information needed to build and maintain living organisms. This is also the scale where quantum effects still play a significant role in determining molecular behavior. Quantum tunneling allows particles to pass through energy barriers that would be insurmountable in classical physics, enabling chemical reactions that would otherwise be impossible. The hydrogen bonds that hold DNA's double helix together rely on quantum mechanical effects, as does the process of photosynthesis that converts sunlight into chemical energy. At the nanoscale, we also encounter the world of nanotechnology, human-engineered structures that rival the molecular machines created by biology. Carbon nanotubes, with their extraordinary strength and electrical properties, graphene sheets just 1 atom thick, and quantum dots that can emit light of precisely controlled colors, all exist at this scale where the properties of matter become exquisitely sensitive to exact atomic arrangements. Moving up to the scale of viruses and large molecules, around 10⁸ meters or 10 nanometers, we find ourselves at the boundary between chemistry and biology. Viruses, existing in the gray area between living and non-living matter, represent some of the most elegant solutions to the problem of storing and transmitting genetic information in the smallest possible package. At this scale, we see how nature has solved the problem of creating complex, functional structures from simple components. Viruses demonstrate how genetic information can be packaged with incredible efficiency. Some viruses contain enough information to hijack a cell's machinery and reproduce themselves, all stored in a package just a few tens of nanometers across. The ribosome, the cellular machine that translates genetic information into proteins, operates at this scale. This ancient molecular machine found in all living cells, represents one of the most sophisticated examples of molecular engineering in nature. The ribosome reads the genetic code written in messenger RNA and translates it into the precise sequence of amino acids needed to build functional proteins. As we continue our journey through the scales, we reach the realm of bacteria and other single-celled organisms at around 10⁶ meters, or 1 micrometer. Here, we encounter the simplest forms of life, organisms that nonetheless contain all the essential machinery needed for life: metabolism, reproduction, and response to environment. At the micrometer scale, we witness the incredible diversity of single-celled life. Bacteria have evolved to thrive in virtually every environment on Earth, from the scalding hot springs of Yellowstone to the frozen depths of Antarctic ice. Some bacteria can survive radiation doses that would be lethal to complex organisms, while others can metabolize chemicals that would be toxic to most life forms. This is the scale where we see how life has learned to harness the fundamental forces of nature for its own purposes. Bacterial flagella, the rotating propellers that allow many bacteria to swim, represent one of the most sophisticated examples of biological engineering, with components that function as rotors, stators, and drive shafts, all assembled with atomic precision. The bacterial cell also demonstrates how life maintains itself far from thermodynamic equilibrium. While non-living systems tend toward disorder and decay, living systems actively maintain their organization through the constant input of energy and the export of entropy. This is life's solution to the second law of thermodynamics: not to violate it, but to create local pockets of order at the expense of increasing disorder in the surrounding environment. Moving up to the scale of human cells, around 10⁵ meters or 10 micrometers, we encounter the basic units of complex life. A typical human cell contains roughly 37 trillion molecular machines, all working together in a precisely orchestrated symphony of chemical reactions. The cell membrane, just a few nanometers thick, serves as both a barrier and a gateway, controlling what enters and exits the cell with remarkable precision. At this scale, we see how life has solved the problem of creating complex, multicellular organisms. Cells specialize, taking on specific roles while maintaining the basic machinery of life. Nerve cells extend long projections to carry electrical signals across the body. Muscle cells contain specialized proteins that can contract and relax, and immune cells patrol the body, identifying and destroying threats. The cell nucleus, containing the organism's genetic information, demonstrates how life has solved the problem of information storage and retrieval. The DNA in a human cell, if stretched out, would be about 2 meters long, yet it's packaged into a nucleus just a few micrometers across. This incredible feat of molecular origami allows cells to access their genetic information while keeping it protected and organized. As we step up another order of magnitude to 10⁴ meters or 100 micrometers, we reach the scale of complex multicellular structures. Here we might find the thickness of a human hair, the diameter of a small blood vessel, or the size of a grain of pollen. This is the scale where we begin to see the emergence of organized tissues and organs. At this scale, we witness how life creates complex structures from simple components. Blood vessels demonstrate how living systems can create efficient transport networks, with arteries, veins, and capillaries forming a branching network that can deliver nutrients and oxygen to every cell in the body. The walls of blood vessels are marvels of biological engineering, able to withstand the pressure of flowing blood while remaining flexible enough to expand and contract with each heartbeat. Plant structures at this scale reveal the elegant solutions evolution has found to the problems of growth, support, and reproduction. The stomata on leaf surfaces, microscopic pores that can open and close to control gas exchange, operate at this scale, allowing plants to balance their need for carbon dioxide with their need to conserve water. This is also the scale where we see the intricate structures that give materials their macroscopic properties. The microstructure of steel, the crystalline arrangements in semiconductors, the fiber patterns in wood, all operate at this scale to determine the properties we observe in everyday materials. Moving up to the millimeter scale, 10 to 3 meters, we reach the realm of small insects, seeds, and other structures that are just visible to the naked eye. At this scale, we encounter some of nature's most impressive examples of miniaturization. Ant brains, containing just a few 100,000 neurons, can nonetheless support complex behaviors including navigation, communication, and social organization. The physics at this scale is dominated by surface effects rather than volume effects. Small insects can walk on water because surface tension forces are strong relative to their weight. They can fall from great heights without injury because air resistance is significant relative to their mass. These scaling effects create a world where the physical rules are subtly different from those we experience at human scales. Seeds at this scale contain all the information and resources needed to grow into complex plants. The remarkable efficiency of biological information storage is evident in seeds. A tiny acorn contains all the genetic information needed to grow into a massive oak tree, along with enough stored energy to support the early stages of growth. As we reach the centimeter scale, 10 to 2 meters, we encounter the world of small animals, large insects, and human-scale structures like fingers and toes. This is the scale where we begin to see complex behaviors emerging from the interaction of simpler components. The flight of a butterfly, the construction of a spider's web, the precise movements of a hummingbird, all demonstrate how complex behaviors can emerge from relatively simple nervous systems. At this scale, we also see how evolution has solved the problem of creating strong, lightweight structures. Bird bones are hollow, like the tubes used in aerospace engineering, providing maximum strength with minimum weight. Insect exoskeletons use the same principle as corrugated cardboard, creating strong structures from minimal material. The centimeter scale is where we see some of nature's most beautiful examples of mathematical principles in action. The spiral arrangements of seeds in a sunflower, the hexagonal cells of a honeycomb, the fractal patterns in fern leaves, all demonstrate how nature has discovered and implemented mathematical solutions to engineering problems. Moving up to the scale of humans and other large animals, around 10 meters or 1 meter, we reach the scale that defines our everyday experience. At this scale, we see how complex, multicellular organisms have solved the problems of structure, movement, and coordination. The human skeleton provides both support and protection, while remaining light enough to allow efficient movement. The human brain, containing roughly 86 billion neurons, represents one of the most complex structures in the known universe. Each neuron can connect to thousands of others, creating a network with trillions of connections. This neural network gives rise to consciousness, memory, emotion, and all the other phenomena we associate with human experience. At the human scale, we also see how intelligence has allowed our species to transcend many of the limitations imposed by biology. Through tools, technology, and culture, humans have extended their capabilities far beyond what their biological heritage would suggest. We can fly faster than birds, see farther than eagles, and communicate across vast distances instantaneously. This is the scale where we see the emergence of culture and civilization. Human societies demonstrate how individual intelligence can be amplified through cooperation and the sharing of knowledge. Cities, languages, art, and science all emerge from the collective efforts of individual humans working together. As we step up to the scale of large animals and small buildings, around 1 meters or 10 meters, we encounter structures that represent the limits of what biology can achieve on land. The largest land animals, elephants, giraffes, and dinosaurs, are constrained by the fundamental physics of scaling. As animals get larger, their volume, and thus their weight, increases as the cube of their linear dimensions, while their bone strength increases only as the square of their linear dimensions. This scaling relationship explains why there are no land animals the size of whales. The skeleton would be too heavy to support the animal's weight. Whales can grow to enormous sizes only because they live in water, where buoyancy helps support their weight. The physics of scaling creates fundamental limits on the size and shape of living organisms. At this scale, we also see how humans have learned to work with and around these scaling laws. Architecture at the 10-meter scale must carefully balance the forces of gravity, wind, and seismic activity. The great cathedrals of Europe, the skyscrapers of modern cities, and the bridges that span rivers and bays all represent human solutions to the engineering challenges imposed by scaling laws. Moving up to the scale of large buildings and small geographical features, around 10.2 meters or 100 meters, we reach the scale where human engineering begins to rival natural structures. The tallest trees, giant sequoias and redwoods, reach heights of over 100 meters, representing the absolute limit of what biological engineering can achieve in terms of vertical structure. At this scale, the physics of fluid flow becomes crucial. Wind patterns around buildings, the flow of water over dam spillways, and the circulation of air through ventilation systems all operate according to the same fluid dynamics principles that govern weather patterns and ocean currents. The interaction between human-built structures and natural forces creates complex feedback loops that can have far-reaching effects. This is also the scale where we see the emergence of complex systems behavior. Traffic flow in cities, the spread of information through social networks, and the dynamics of financial markets all demonstrate how simple rules governing individual behavior can give rise to complex, emergent patterns at larger scales. As we continue our journey outward, we reach the scale of neighborhoods and small towns, around 10.3 meters or 1 kilometer. At this scale, we see how human communities organize themselves in space. The layout of cities reflects the interplay between geography, technology, and social forces. Rivers, hills, and other natural features constrain urban development, while transportation networks, roads, railways, and airports enable it. The kilometer scale is where we begin to see the effects of human activity on natural systems. Urban heat islands, caused by the concentration of concrete and asphalt, can raise local temperatures by several degrees. The channeling of water through storm drains and sewers alters local hydrology, while the concentration of traffic and industry affects air quality. At this scale, we also see how human systems have evolved to manage complexity. Cities require sophisticated systems for delivering water, electricity, and communications to millions of people. These infrastructure networks represent some of the most complex engineering systems ever created, with millions of components that must work together reliably. Moving up to the scale of large cities and geographical regions around 10⁴ meters or 10 kilometers, we encounter systems that span multiple human communities. Metropolitan areas demonstrate how human settlement patterns reflect the interaction between economic, social, and technological forces. The concentration of people and resources in cities creates opportunities for specialization and innovation, but also challenges related to resource management and environmental impact. At this scale, natural systems begin to dominate human-built structures. Mountain ranges, river systems, and weather patterns operate at scales that dwarf human engineering projects. The watershed of a major river can span thousands of square kilometers, collecting water from vast areas and channeling it toward the sea. This is the scale where we see the emergence of regional ecosystems. Forests, grasslands, and wetlands form complex webs of interdependent species, with energy and nutrients flowing through food webs that can include hundreds or thousands of different organisms. The stability of these ecosystems depends on the maintenance of delicate balances between predators and prey, between different plant species competing for sunlight and nutrients. As we step up to the scale of small countries and major geographical features around 5 meters or 100 kilometers, we reach the scale where geological processes become apparent. Mountain ranges, formed by the collision of tectonic plates over millions of years, represent some of the most dramatic examples of the Earth's geological history written in stone. At this scale, we see how climate patterns are influenced by geography. Mountain ranges create rain shadows, blocking moisture-laden air and creating deserts on their leeward sides. Ocean currents, driven by temperature differences and the Earth's rotation, transport heat around the globe, moderating climate in some regions while creating extreme conditions in others. This is also the scale where we see the full extent of human impact on the natural world. Deforestation, urbanization, and agriculture have transformed vast areas of the Earth's surface. From space, the geometric patterns of human agriculture are clearly visible, creating a patchwork of fields and settlements that extends across entire continents. The 100-kilometer scale is where we begin to see the curvature of the Earth. The horizon, which seems flat from ground level, begins to show its true curved nature when viewed from high altitudes. This is the scale where early astronomers first began to suspect that the Earth might be spherical rather than flat. Moving up to the scale of large countries and continents, around 10⁶ meters or 1,000 kilometers, we reach the scale where the Earth's spherical nature becomes undeniable. Continental scale features, the Great Plains of North America, the Amazon rainforest, the Sahara Desert, demonstrate how geological and climatic processes operate over vast areas and long time scales. At this scale, we see how the Earth's systems are interconnected. The Amazon rainforest affects rainfall patterns thousands of kilometers away. Volcanic eruptions can inject ash and sulfur compounds into the atmosphere, affecting global climate for years. The circulation of ocean currents transports heat, nutrients, and marine life around the globe. This is the scale where we see the full extent of human civilization. From space, the networks of cities, roads, and agricultural areas clearly reveal the presence of an intelligent, technological species. The lights of cities, visible from orbit, create a glowing web that outlines the continents and reveals the distribution of human population. Continental scale systems also demonstrate how human activities can have global effects. The emission of greenhouse gases from one continent affects climate worldwide. The depletion of ozone over Antarctica affects ultraviolet radiation levels around the globe. At this scale, it becomes clear that human activity must be understood as a global phenomenon. As we reach the scale of the entire Earth, around 10⁻⁷ meters or 10,000 kilometers in diameter, we encounter our home planet as a single integrated system. From this perspective, the Earth reveals itself as a thin shell of rock surrounding a molten core, with a gossamer-thin atmosphere that contains all the air we breathe and all the weather we experience. The Earth system demonstrates how seemingly separate processes are actually interconnected. The carbon cycle links the atmosphere, oceans, land surface, and living organisms in a complex web of feedbacks. Water cycles between the oceans, atmosphere, and land, driving weather patterns and supporting all terrestrial life. The nitrogen cycle, mediated by bacteria and other microorganisms, makes this essential element available to plants and animals. At the planetary scale, we see how rare and precious our living world truly is. The Earth occupies a narrow Goldilocks zone around the Sun. Not too hot, not too cold, but just right for liquid water to exist on the surface. This habitability depends on a delicate balance of factors: the Earth's distance from the Sun, its atmospheric composition, its magnetic field, and its geological activity. The Earth's magnetic field, generated by the motion of molten iron in the planet's core, creates a protective shield that deflects most of the charged particles streaming from the Sun. Without this magnetic protection, the solar wind would gradually strip away our atmosphere, as appears to have happened to Mars billions of years ago. From the planetary perspective, we can see how life has shaped the Earth's environment. The oxygen in our atmosphere is largely the product of photosynthesis by plants and algae. The composition of our oceans has been influenced by the shells and skeletons of marine organisms. Life and environment have co-evolved over billions of years, each shaping the other in an intricate dance of mutual influence. This concludes the first half of our journey through the scales of the universe. We've traveled from the quantum foam at the Planck scale to our entire planet Earth, spanning 21 orders of magnitude. Each step has revealed new levels of complexity, new physical phenomena, and new ways of understanding the interconnectedness of all things. In the second half of our journey, we'll continue outward from Earth, exploring the scale of the solar system, nearby stars, our galaxy, and ultimately, the observable universe itself. We'll discover how the same physical laws that govern quantum particles also shape the largest structures in the cosmos, and how the universe reveals its deepest secrets to those patient enough to contemplate its vast scales. The journey we've taken so far has shown us that we exist at a unique position in the cosmic hierarchy of scales, large enough to contemplate the quantum world beneath us, yet small enough to marvel at the astronomical scales above us. We are, in the words of astronomer Carl Sagan, a way for the cosmos to know itself. In the second half of our journey, we'll explore the cosmic scales that dwarf even our entire planet and contemplate our place in the infinite expanse of space and time. As we continue our journey through the cosmic scales, we leave behind the familiar realm of our planet Earth and venture into the vast emptiness of space. Here, the scales become so large that they challenge our ability to comprehend them. Yet each step reveals new wonders and deepens our understanding of the universe we inhabit. Stepping up from planetary scales to the realm of the inner solar system, around 10⁸ meters or 100,000 kilometers, we encounter distances where the concept of traveling becomes fundamentally different. At this scale, light itself, the fastest thing in the universe, takes a noticeable amount of time to traverse the distance. Light from the Moon takes about 1.3 seconds to reach Earth, while communication signals to spacecraft orbiting at this distance experience delays that become operationally significant. This is the scale where we first encounter the vast emptiness that characterizes most of the universe. The space between the Earth and Moon contains virtually nothing, just a few hydrogen atoms per cubic centimeter, along with the occasional charged particle from the solar wind. This emptiness is more perfect than any vacuum we can create in Earth-based laboratories, yet it's filled with invisible fields, gravitational, magnetic, and electromagnetic, that connect distant objects across the void. At this scale, we see how gravitational forces shape the architecture of space. The Moon's gravity creates tides on Earth, raising and lowering the oceans twice each day in a rhythm that has persisted for billions of years. This gravitational dance has gradually slowed the Earth's rotation and increased the distance to the Moon, demonstrating how even the most apparently stable celestial arrangements are slowly evolving over cosmic time. The Earth-Moon system also reveals how angular momentum, the tendency of rotating objects to keep rotating, is conserved on cosmic scales. As the Earth's rotation slows due to tidal friction, the Moon gradually moves farther away, maintaining the total angular momentum of the system. This process will continue for billions of years until the Earth and Moon become tidally locked, always showing the same face to each other. Moving outward to the scale of the inner solar system, around 10⁹ meters or 1 million kilometers, we reach distances comparable to the diameter of the Sun. At this scale, we begin to appreciate the true size of our nearest star. The Sun contains 99.86% of all the mass in the solar system, and its gravitational influence extends far beyond its visible surface. The Sun's magnetic field, generated by the complex motions of plasma in its interior, creates a dynamic, ever-changing environment that affects the entire solar system. Solar flares and coronal mass ejections send billions of tons of charged particles streaming through space at speeds of hundreds of kilometers per second. When these particles interact with planetary magnetic fields and atmospheres, they create phenomena like the aurora that remind us of our connection to the larger cosmic environment. At this scale, we also encounter the realm of artificial satellites and space debris. The growing population of human-made objects in Earth orbit demonstrates how our species has begun to extend its presence beyond the surface of our home planet. Communications satellites, weather monitoring systems, and scientific instruments have created a technological shell around the Earth, enabling global communications and advancing our understanding of both our planet and the cosmos beyond. The million-kilometer scale is where we see how the interplay between gravitational and electromagnetic forces creates the complex dynamics of the solar wind and interplanetary magnetic field. The Sun's rotation creates a spiral pattern in its magnetic field, like water spraying from a rotating sprinkler, that extends throughout the solar system and influences the movement of charged particles in interplanetary space. Stepping up to 10⁻10 meters, or 10 million kilometers, we reach the scale where the orbits of the inner planets become apparent. At this distance, we can begin to see the solar system as an organized structure, with planets following elliptical paths around the central sun in a cosmic dance that has continued for over 4 billion years. Mercury, the innermost planet, completes its orbit at this scale in just 88 Earth days, traveling at an average speed of 48 kilometers per second. The extreme conditions on Mercury, with surface temperatures ranging from 427 degrees on the day side to 173 degrees on the night side, demonstrate how planetary environments are shaped by their distance from the Sun and their orbital characteristics. At this scale, we see how the inverse square law governs the intensity of sunlight and the strength of gravitational forces. Venus, despite being farther from the Sun than Mercury, is actually hotter due to its thick carbon dioxide atmosphere that creates a runaway greenhouse effect. This serves as a powerful reminder of how atmospheric composition can dramatically affect planetary climate. The 10 million kilometer scale is also where we encounter some of the most dramatic examples of gravitational dynamics in the solar system. Close approaches between asteroids and planets can result in orbital changes that send objects careening through the inner solar system. The asteroid belt, located between Mars and Jupiter, contains remnants from the early solar system that never coalesced into a planet, possibly due to gravitational disruption from nearby Jupiter. Moving outward to 10 or 11 meters, or 100 million kilometers, we reach the scale of the Earth's orbit around the Sun. This distance, known as an astronomical unit, AU, serves as our fundamental ruler for measuring distances within the solar system. At this scale, light from the Sun takes about 8 minutes and 20 seconds to reach Earth, meaning that we always see the Sun as it was 8 minutes ago. The Earth's orbital distance places it within the habitable zone, or Goldilocks zone, around the Sun, the region where liquid water can exist on a planetary surface. This zone extends roughly from 0.95 to 1.37 AU from the Sun, encompassing Earth's orbit and extending partway into the asteroid belt. The existence of this habitable zone is one of the key factors that has allowed life to develop and flourish on our planet. At the AU scale, we see how orbital mechanics govern the motion of planets and smaller bodies throughout the solar system. Kepler's laws, discovered in the early 17th century, reveal the mathematical relationships that govern planetary orbits. The square of a planet's orbital period is proportional to the cube of its average distance from the Sun, a relationship that holds with extraordinary precision for all objects orbiting the Sun. This scale also reveals the subtle gravitational influences that shape planetary orbits over long time periods. The gravitational pull of other planets causes small perturbations in Earth's orbit that change over cycles of tens of thousands of years. These Milankovitch cycles affect the amount and distribution of solar energy reaching Earth's surface, contributing to long-term climate changes, including ice ages. The dynamics at the AU scale demonstrate how the solar system is a finely tuned gravitational machine. The spacing of planetary orbits follows patterns that suggest complex interactions during the early formation of the solar system. The Grand Tack model suggests that Jupiter migrated inward and then outward during the solar system's formation, preventing the formation of a large planet in the asteroid belt and allowing the small, rocky planets of the inner solar system to form. Stepping up to 12 meters, or 10 AU, we encompass the orbits of the outer planets and enter the realm of the giant worlds. Jupiter, the largest planet in our solar system, orbits at an average distance of 5.2 AU from the Sun, while Saturn orbits at 9.5 AU. At these distances, the Sun appears as a much smaller, dimmer disk, providing far less energy per unit area than it does to the inner planets. The outer planets reveal how different planetary formation processes created worlds utterly unlike the rocky inner planets. Jupiter and Saturn are primarily composed of hydrogen and helium, the same elements that make up the Sun, while Uranus and Neptune contain large amounts of water, methane, and ammonia ices. These gas and ice giants formed in the outer regions of the solar nebula where temperatures were low enough for volatile compounds to condense. Jupiter's immense gravitational influence has earned it the nickname the solar system's vacuum cleaner. Its gravity captures or deflects many comets and asteroids that might otherwise threaten the inner planets. The Shoemaker-Levy 9 comet impact in 1994 provided a dramatic demonstration of Jupiter's protective role, as the giant planet absorbed the impact of multiple comet fragments, each releasing energy equivalent to millions of nuclear weapons. At the 10 AU scale, we also encounter the complex systems of moons that orbit the giant planets. Jupiter's 4 largest moons, Io, Europa, Ganymede, and Callisto, form a miniature solar system in their own right. These Galilean moons, discovered by Galileo in 1610, demonstrate how tidal forces from the central body can drive geological activity on satellites. Io's volcanic activity is powered by the gravitational stretching it experiences in its elliptical orbit around Jupiter. The ring systems of the giant planets reveal how gravitational forces can organize matter into elegant geometric patterns. Saturn's rings, composed primarily of water ice particles ranging in size from dust grains to house-sized boulders, demonstrate how gravitational resonances with moons can create gaps in structure within the ring system. The Cassini division, a prominent gap in Saturn's rings, is maintained by gravitational resonances with Saturn's moon mₑ². Moving outward to 10⁻13 meters, or 100 AU, we reach the edge of the solar system's planetary region and enter the realm of the Kuiper Belt. This region, extending from about 30 to 50 AU from the Sun, contains thousands of icy bodies left over from the solar system's formation. Pluto, reclassified as a dwarf planet in 2006, orbits within this region, along with other notable objects like Eris, mₑ², and Haumea. The Kuiper Belt objects provide crucial insights into the early history of our solar system. These primitive bodies have remained largely unchanged since their formation 4.6 billion years ago, preserving a record of the conditions and processes that existed in the outer solar nebula. The discovery of many Kuiper Belt objects with similar orbital characteristics suggests that the outer solar system underwent a period of dynamical instability early in its history, possibly triggered by the migration of the giant planets. At this scale, the Sun appears as just another star, bright, but no longer the overwhelming presence it is from Earth's perspective. The solar wind, which creates the tenuous solar atmosphere that extends throughout the planetary region, begins to weaken significantly at these distances. The heliopause, where the solar wind meets the interstellar medium, lies at roughly 120 AU from the Sun, marking the true boundary of the solar system's influence. This is also the scale where we encounter some of the most distant human-made objects. The Voyager 1 and 2 spacecraft, launched in 1977, have traveled beyond 100 AU from the Sun and continue to send back data about the outer reaches of the solar system. Voyager 1 crossed the heliopause in 2012, becoming the first human-made object to enter interstellar space, though it remains gravitationally bound to the Sun. The 100 AU scale reveals how the solar system exists within a much larger galactic environment. The motion of the solar system through the galaxy exposes it to varying densities of interstellar matter, which can affect the size and shape of the heliosphere over time scales of millions of years. The solar system is currently passing through a region of relatively low-density interstellar space called the local bubble, created by ancient supernova explosions. Stepping up to 10⁻14 meters, or 1000 AU, we encounter the Oort cloud, a spherical shell of icy objects that surrounds the solar system at distances ranging from about 2,000 to 100,000 AU. This vast reservoir of comets contains perhaps 1 trillion or more objects, representing the most distant gravitationally bound members of our solar system. The Oort cloud demonstrates how the solar system's gravitational influence extends far beyond the planetary region. Objects in the Oort cloud have orbital periods measured in millions of years, and their orbits can be perturbed by the gravitational influence of passing stars or giant molecular clouds in the galaxy. When these perturbations send Oort cloud objects toward the inner solar system, they become the long-period comets that occasionally grace our skies. At this scale, we begin to see how the solar system interacts with its galactic environment. The Sun's motion through the galaxy, combined with the galaxy's rotation, subjects the Oort cloud to tidal forces that can strip away its outermost members over geological time scales. Stars that pass close to the solar system can gravitationally disturb the Oort cloud, potentially triggering comet showers that increase the impact rate on the inner planets. The 1000 AU scale is where the concept of stellar distances begins to become meaningful. The nearest star to the Sun, Proxima Centauri, lies at a distance of about 270,000 AU or 24 light-years. At this scale, interstellar space reveals itself to be unimaginably vast, with typical distances between stars measured in light-years rather than astronomical units. This scale also marks the transition from solar system astronomy to stellar astronomy. While the Sun's gravity still dominates the motion of Oort cloud objects, the gravitational influence of other stars becomes increasingly important at larger distances. The boundary between the solar system and interstellar space is not sharp, but gradual, with the Sun's influence slowly giving way to the combined gravitational field of all the stars in the galaxy. Moving up to 10-15 meters, or roughly 1 light-year, we enter the realm of interstellar space. At this scale, the Sun becomes just one star among many, and we begin to appreciate the true scale of our galaxy. 1 light-year, the distance light travels in 1 year, equals about 9.46 trillion kilometers, or 63,000 AU. This is the natural unit for measuring stellar distances. The interstellar medium at this scale reveals itself to be far from empty. Between the stars lies a tenuous mix of gas and dust, with typical densities of about 1 atom per cubic centimeter. This may seem like a perfect vacuum by terrestrial standards, but it represents an enormous amount of matter when integrated over galactic scales. The interstellar medium contains roughly 10% of the galaxy's visible matter. At the light-year scale, we encounter the beautiful and complex structures created by stellar evolution. Planetary nebulae, formed when dying stars shed their outer layers, create expanding shells of glowing gas that can span several light-years. These nebulae reveal the chemical enrichment process by which stars return processed material to the interstellar medium, seeding space with the heavy elements necessary for planet formation and life. Supernova remnants at this scale demonstrate the violent end of massive stars and their profound impact on the surrounding interstellar medium. The Crab Nebula, the remnant of a supernova observed by Chinese astronomers in 1054 CE, spans about 11 light-years and continues to expand at speeds of over 1,000 kilometers per second. The shock waves from supernovae can trigger the formation of new stars by compressing nearby gas clouds. The light-year scale is also where we see the effects of stellar winds and radiation on the interstellar environment. Massive hot stars create cavities in the interstellar medium through their intense stellar winds and ultraviolet radiation. These stellar bubbles can span tens of light-years and reveal the complex feedback mechanisms by which stars affect their galactic environment. Stepping up to 10 16 meters or 10 light-years, we reach the scale of stellar neighborhoods and begin to see the local structure of our galaxy. Within 10 light-years of the Sun lie only a handful of other stars, including the Alpha Centauri system, Barnard's star, and several red dwarf stars. This local stellar density is typical for our region of the galaxy, with an average of about 1 star per 300 cubic light-years. At this scale, we can begin to trace the Sun's motion through the galaxy and its interactions with nearby stars. The Sun orbits the galactic center at a speed of about 220 kilometers per second, completing one orbit roughly every 225 million years. This galactic year provides a new perspective on Earth's history. Complex life has existed for only the most recent galactic year, while the solar system itself has completed about 20 orbits since its formation. The 10 light-year scale reveals how stellar motions create an ever-changing local stellar environment. Stars have their own peculiar velocities relative to the average motion of stars in the galaxy, causing them to move relative to each other over time. About 1.3 million years ago, the red dwarf star Schultz's star passed within about 0.8 light-years of the Sun, possibly disturbing the outer Oort cloud and triggering a shower of comets. This scale also encompasses some of the nearest star-forming regions, where we can observe the birth of new stellar systems. The Taurus Auriga complex, located about 140 parsecs, 460 light-years away, contains numerous young stars and protostars embedded in dark molecular clouds. These star-forming regions provide insights into how the solar system itself may have formed billions of years ago. At the 10 light-year scale, we also begin to see the effects of the interstellar magnetic field. This weak but pervasive field, typically about 100,000 times weaker than Earth's magnetic field, nevertheless plays a crucial role in the dynamics of the interstellar medium and the formation of stars. The magnetic field can support gas clouds against gravitational collapse and influence the flow of charged particles through interstellar space. Moving up to 10 17 meters or 100 light-years, we reach the scale where the disk structure of our galaxy becomes apparent. At this scale, we can see how stars are not uniformly distributed through space, but are concentrated in a flattened disk with spiral arms that wind around the galactic center. Our solar system lies within the Orion Arm, a minor spiral arm located between the major Perseus and Sagittarius arms. The 100 light-year scale reveals the complex ecology of stellar birth and death within our galaxy. Giant molecular clouds, the birthplaces of stars, can span hundreds of light years and contain enough material to form thousands of new stars. These clouds are not permanent features, but evolve over millions of years, forming stars that eventually disrupt and disperse the remaining gas. At this scale, we encounter some of the most spectacular stellar phenomena in our galaxy. Wolf-Rayet stars, massive stars in their final evolutionary stages, create expanding bubbles of hot gas that can span hundreds of light years. These stars are so massive and luminous that they can be detected across the entire galaxy, serving as beacons that reveal the structure of distant spiral arms. The 100 light-year scale is also where we see the effects of supernova explosions on galactic structure. A single supernova can create a hot bubble in the interstellar medium that expands for millions of years, potentially merging with bubbles from other supernovae to create vast cavities called superbubbles. These structures can span hundreds of light years and significantly affect the distribution of gas and dust in the galaxy. This scale encompasses the local bubble, a cavity in the interstellar medium that surrounds the solar system and extends for several hundred light years in all directions. This bubble was likely created by multiple supernova explosions over the past 10-20 million years, clearing out much of the interstellar material in our local region and creating the relatively empty space through which the solar system currently moves. Stepping up to 10 or 18 meters, or 1,000 light years, we reach the scale where the three-dimensional structure of our galaxy becomes clearly visible. At this scale, we can see how the galactic disk has a complex structure with spiral arms, star-forming regions, and vast cavities created by stellar activity. The thickness of the galactic disk becomes apparent, about 1,000 light-years for the thin disk where most stars reside. The kiloparsec scale, 1,000 light-years equals about 0.3 kiloparsecs, reveals the grand design of spiral structure in our galaxy. The spiral arms are not rigid structures, but rather density waves that propagate through the galactic disk, compressing gas and triggering star formation as they pass. This explains why the spiral arms are outlined by bright, massive stars and star-forming regions. These young, luminous objects trace the recent passage of the spiral density wave. At this scale, we encounter some of the galaxy's most prominent star-forming regions. The Cygnus X complex, located about 1,400 parsecs away, is one of the most active star-forming regions in our galaxy, containing numerous massive stars, stellar clusters, and nebulae. These regions demonstrate how star formation occurs in a hierarchical fashion, with molecular clouds fragmenting into smaller clumps that eventually form individual stars and stellar clusters. The 1,000 light-year scale is also where we see the effects of galactic rotation on the interstellar medium. The differential rotation of the galaxy, the fact that stars at different distances from the center orbit at different speeds, creates shear forces that can stretch and distort gas clouds and magnetic field lines. This galactic shear plays a crucial role in the formation and evolution of spiral structure. This scale encompasses the vertical structure of the galactic disk, including the thin disk where most stars are found and the thick disk containing older stellar populations. The halo of our galaxy, containing globular clusters and individual halo stars, also becomes visible at this scale. These different galactic components tell the story of our galaxy's formation and evolution over billions of years. Moving up to 10⁻19 meters, or 10,000 light-years, we reach the scale where our entire galaxy begins to reveal its overall structure. The Milky Way galaxy is a barred spiral galaxy with a diameter of about 100,000 light-years. At this scale, we can see the galaxy's central bar, spiral arms, and the spherical halo that surrounds the disk. The 10 kiloparsec scale reveals the Milky Way's place within the local group of galaxies. Our galaxy, along with the Andromeda Galaxy and about 50 smaller galaxies, forms a gravitationally bound system spanning several million light-years. The local group demonstrates how galaxies are not isolated island universes, but exist within a complex web of gravitational relationships. At this scale, we encounter phenomena that operate on galactic scales. The galactic center, located about 26,000 light-years from the Sun, contains a supermassive black hole with a mass of about 4 million solar masses. This black hole, known as Sagittarius A, occasionally accretes material and produces high-energy radiation that can be detected throughout the galaxy. The 10,000 light-year scale is where we see the effects of galactic dynamics on stellar populations. The galaxy's rotation curve, the relationship between orbital velocity and distance from the center, provides crucial evidence for the existence of dark matter. The observed rotation curve cannot be explained by the visible matter alone, requiring the presence of a massive dark matter halo, extending well beyond the visible disk. This scale also encompasses the galaxy's magnetic field structure. The galactic magnetic field, though weak, plays a crucial role in the dynamics of the interstellar medium and the propagation of cosmic rays. The field lines generally follow the spiral arms, but show complex structure on smaller scales, influenced by stellar winds, supernova explosions, and turbulent motions in the interstellar gas. Stepping up to 10^20 meters, or 100,000 light-years, we encompass the entire visible extent of our galaxy. At this scale, the Milky Way reveals itself as a majestic spiral galaxy with well-defined arms, a central bulge, and an extended halo. The galaxy contains about 100 to 400 billion stars, making it a typical large spiral galaxy. The 100,000 light-year scale is where we can study our galaxy as a complete system and compare it to other galaxies in the universe. The Milky Way is part of a class of galaxies known as SB or SBB, barred spirals, characterized by well-developed spiral arms and significant disk-to-bulge ratios. Understanding our galaxy's structure and evolution provides insights into galaxy formation and evolution throughout the universe. At this scale, we see how the galaxy exists within the context of the larger cosmic web. The Milky Way is falling toward the Andromeda Galaxy at a speed of about 110 kilometers per second, and the two galaxies are expected to merge in about 4.5 billion years. This future merger will create a new elliptical galaxy, sometimes nicknamed mₑ². The galactic scale also reveals the importance of dark matter in galactic structure. The visible matter in the galaxy, stars, gas, and dust, accounts for only about 15% of the galaxy's total mass. The remaining 85% consists of dark matter, which can only be detected through its gravitational effects. This dark matter halo extends well beyond the visible galaxy and plays a crucial role in the galaxy's formation and evolution. The 100,000 light-year scale encompasses the galaxy's globular cluster system. These ancient stellar clusters, some containing over 1 million stars, orbit the galaxy in the halo and provide insights into the early history of galaxy formation. The ages and chemical compositions of globular cluster stars indicate that the galaxy's halo formed over 10 billion years ago, making it one of the oldest components of the galaxy. Moving up to 10 powers of 21 meters, or 1 million light-years, we enter the realm of galaxy groups and begin to see the Milky Way's place within the larger structure of the universe. The local group, containing the Milky Way, Andromeda, and their satellite galaxies, spans about 10 million light-years and represents a typical small galaxy group in the universe. At the megaparsec scale, 1 million light-years equals about 0.3 megaparsecs, we see how galaxies are not randomly distributed through space, but exist within a hierarchical structure of groups, clusters, and larger assemblages. The local group is itself part of a larger structure called the local supercluster or Virgo supercluster, which contains thousands of galaxies spread across about 100 million light-years. The million light-year scale reveals the importance of gravitational interactions between galaxies. Tidal forces between galaxies can trigger starbursts, distort galactic structure, and even strip away gas and stars from smaller galaxies. The Magellanic Clouds, satellite galaxies of the Milky Way, show clear evidence of tidal disruption, with streams of stars and gas connecting them to our galaxy. This scale also encompasses the intergalactic medium, the tenuous gas that exists between galaxies. This medium, though extremely sparse, contains the majority of the ordinary matter in the universe. The intergalactic medium plays a crucial role in galaxy formation and evolution, providing the raw material from which galaxies form, and continuing to feed their growth over cosmic time. At the million light-year scale, we begin to see the effects of cosmic expansion on galactic motions. While gravity dominates on smaller scales, keeping galaxy groups bound together, the expansion of space itself becomes important on larger scales. The recession velocities of distant galaxies, first observed by Edwin Hubble in the 1920s, provided the first evidence for the expansion of the universe. Stepping up to 10 pounds and 22 meters, or 10 million light-years, we reach the scale of galaxy clusters, some of the largest gravitationally bound structures in the universe. The Virgo cluster, located about 50 million light-years away, contains over 1,000 galaxies and has a total mass of about 10 from 15 solar masses. Such clusters represent the nodes where the cosmic web's filaments intersect. The 10 megaparsec scale reveals how galaxy evolution is strongly influenced by environment. Galaxies in dense cluster environments undergo different evolutionary processes than those in less dense regions. The hot, dense intracluster medium can strip gas from galaxies through ram pressure stripping, shutting down star formation and transforming spiral galaxies into ellipticals. At this scale, we encounter some of the most energetic phenomena in the universe. Active galactic nuclei, powered by supermassive black holes, can outshine entire galaxies and influence the evolution of their host clusters. Radio galaxies can create jets of high-energy particles that extend for millions of light-years, creating vast lobes of radio emission that dwarf the visible galaxy. The 10 million light-year scale is where we see clear evidence for dark matter on cosmic scales. Galaxy clusters contain much more mass than can be accounted for by their visible galaxies and hot gas. Gravitational lensing observations, which measure how clusters bend light from background galaxies, provide direct evidence for the presence of large amounts of dark matter in clusters. This scale also reveals the process of structure formation in the universe. Computer simulations show how dark matter halos grow through accretion and mergers, with smaller halos eventually becoming part of larger structures. The observed distribution of galaxy clusters matches the predictions of these simulations, providing strong support for our understanding of cosmic structure formation. Moving up to 10,023 meters, or 100 million light-years, we reach the scale of superclusters, vast assemblages of galaxy clusters connected by filaments of galaxies and dark matter. The local supercluster, containing our local group, along with the Virgo cluster and many other galaxy groups, spans about 100 million light-years. At the 100 megaparsec scale, the cosmic web becomes clearly visible. This web-like structure, composed of filaments of dark matter and galaxies separated by vast voids, represents the largest scale structure in the universe. The cosmic web emerged from tiny quantum fluctuations in the early universe, amplified by billions of years of gravitational growth. The supercluster scale reveals how the universe has evolved from an initially smooth distribution of matter to the highly structured cosmos we observe today. The pattern of structure formation follows a hierarchical model, with smaller structures forming first and later assembling into larger ones. This process continues today, with galaxy clusters still growing through the accretion of smaller groups and individual galaxies. At this scale, we also see the effects of cosmic expansion more clearly. While superclusters are held together by gravity, the expansion of space causes them to grow larger over time. The recession velocities of distant galaxies become substantial, requiring corrections for relativistic effects when measuring distances and calculating the expansion rate. The 100 million light-year scale encompasses some of the largest coherent structures known in the universe. The Great Wall, a sheet-like structure of galaxies discovered in the 1980s, extends for over 500 million light-years. Such structures approach the theoretical limits of how large gravitationally assembled objects can be in our universe. Stepping up to 10,024 meters, or 1 billion light-years, we reach the scale where the universe begins to appear homogeneous and isotropic on the largest scales. This is the scale of the cosmic microwave background radiation, which shows us the universe as it was about 380,000 years after the Big Bang, when it first became transparent to light. The billion light-year scale reveals the fundamental properties of our universe. Observations of Type Ia supernovae at these distances provided the first evidence that the expansion of the universe is accelerating, driven by a mysterious component called dark energy. This discovery, made in 1998, revolutionized our understanding of the universe's composition and fate. At this scale, we see how the universe's large-scale structure relates to the initial conditions present shortly after the Big Bang. The tiny temperature fluctuations observed in the cosmic microwave background, variations of only about 10⁵ in temperature, represent the seeds from which all cosmic structure eventually grew. The pattern of these fluctuations matches the predictions of inflation theory, providing strong evidence for this model of the early universe. The billion light-year scale is where we encounter the concept of the cosmic horizon, the maximum distance from which light has had time to reach us since the Big Bang. This horizon grows with time as the universe ages, but it also sets a fundamental limit on how far we can observe into the universe. Objects beyond this horizon are fundamentally unobservable, regardless of the power of our telescopes. At this scale, we also see the effects of cosmic time dilation. Light from distant galaxies shows us these objects as they were billions of years ago, when the universe was much younger. The most distant galaxies observed today appear as they were when the universe was only about 5% of its current age, providing a fossil record of cosmic evolution. Moving up to 10⁻25 meters, or 10 billion light-years, we approach the edge of the observable universe and encounter phenomena from the early epochs of cosmic history. At these distances, we observe galaxies as they were when the universe was only 1–2 billion years old, revealing the processes of early galaxy formation and evolution. The 10 billion light-year scale encompasses the era of peak star formation in the universe, when galaxies were forming stars at rates much higher than observed today. These early galaxies appear smaller and more irregular than their modern counterparts, reflecting the ongoing process of galaxy assembly through mergers and accretion. At this scale, we encounter quasars, the most luminous objects in the universe. These active galactic nuclei, powered by supermassive black holes, accreting matter at prodigious rates, can outshine entire galaxies by factors of thousands. The most distant quasars observed provide insights into the formation of the first supermassive black holes in the early universe. The 10 billion light-year scale also reveals the chemical evolution of the universe. Early galaxies contain much lower abundances of heavy elements than local galaxies, reflecting the fact that these elements are produced in stars and dispersed through supernova explosions over cosmic time. The metallicity evolution of galaxies provides important constraints on models of star formation and chemical enrichment. This scale encompasses the epoch of rayonization, when the first stars and galaxies produced enough ultraviolet radiation to ionize the neutral hydrogen that filled the universe after the cosmic microwave background was emitted. This phase transition, occurring roughly 150 million to 1 billion years after the Big Bang, marked the end of the cosmic dark ages and the beginning of the universe's current transparent state. Finally, reaching 10,026 meters, or roughly 100 billion light-years, we approach the scale of the entire observable universe. This represents the maximum distance from which light has had time to reach us since the Big Bang occurred about 13.8 billion years ago. Due to the expansion of space, objects at this distance have actually receded to much greater distances, perhaps 46 billion light-years away. At this ultimate scale, we see the universe as a whole, a vast, expanding cosmos filled with billions of galaxies, each containing billions of stars. The observable universe contains an estimated 1022 to 10⁻24 stars, a number so large it exceeds the number of grains of sand on all the beaches of Earth. The scale of the observable universe reveals the profound mystery of cosmic inflation. The universe appears remarkably homogeneous on the largest scales, with the same temperature and density in regions that should never have been in causal contact. Inflation theory explains this by proposing that the universe underwent a period of exponential expansion in its earliest moments, stretching tiny, causally connected regions to cosmic scales. At this ultimate scale, we also confront the limits of our knowledge. The observable universe may be only a tiny fraction of the entire universe, which could be infinite in extent. The cosmic microwave background provides our best window into the early universe, but it represents an opaque wall beyond which we cannot directly observe. The journey from the Planck length to the observable universe has taken us through 61 orders of magnitude, a range of scales so vast that it challenges our comprehension. Yet this journey reveals the deep interconnectedness of all scales in the universe. The quantum fluctuations that operate at the smallest scales may have seeded the largest structures in the cosmos. The same physical laws that govern the behavior of atoms also determine the motion of galaxies and the expansion of space itself. As we conclude this cosmic journey, we find ourselves poised between the infinitely small and the infinitely large, citizens of a universe whose scale and complexity inspire both humility and wonder. We are made of atoms, forged in the hearts of dying stars, living on a planet orbiting an ordinary star in a typical galaxy, part of a cosmic web that stretches across billions of light years. We are, in Carl Sagan's beautiful phrase, the universe becoming aware of itself. The scales we have explored tonight remind us that we exist at a unique position in the cosmic hierarchy, large enough to contemplate the quantum realm, yet small enough to marvel at the vast cosmos that surrounds us. In understanding these scales, we gain not just knowledge of the universe, but perspective on our own place within it. Close your eyes now and let your mind drift across these cosmic scales. Feel yourself floating in the vast spaces between galaxies, drifting past clusters and superclusters, through the cosmic web of dark matter and light. Let the immensity wash over you, bringing not anxiety, but peace. The deep peace that comes from understanding our place in the infinite cosmos. You are part of this vast, beautiful universe, connected to every scale from the quantum to the cosmic. As you drift towards sleep, carry with you this sense of cosmic perspective, this awareness of the incredible journey from the smallest possible measurement to the largest structures we can observe. In sleep, your mind can wander freely through these scales, exploring realms of space and time that dwarf our everyday concerns. Rest now in the knowledge that you are made of star stuff, temporary arrangements of atoms that will one day return to the cosmic dance, but for now are gathered together in the remarkable form of a conscious being capable of contemplating the universe itself. Let the vastness of cosmic scales bring you peace, perspective, and the deep sleep that comes from understanding your place in the infinite cosmos.